Okay, so now that we've talked about organic compounds and we've started to name some basic things, let's talk about how these things sort of behave when they come together. So when we talk about the properties of organic compounds, what we're talking about is what does like a cup of this stuff feel like? What does it act like? And how do those different carbons interact with each other? Do they stick together really well? Do they not stick together really well? That's what we mean by properties. And that can actually tell us some trends that we can look for. For example, melting points and boiling points are affected by what type of compound you have there. You remember how, I hope in the previous courses, you've looked at how ionic bonds are between metal and nonmetal. So this is an actual positive charge, negative charge. So that's kind of like a magnet. Things stick together really, really well, right? Dipole interactions with ions tend to be pretty good. Hydrogen bonds, those are really strong. That's what keeps water bound together so well. Dipole-dipole interactions are there. And with alkanes and simple stuff like just carbon and hydrogen, we have nonpolar interactions there. So it's not as if there's a lot of sticky together. They're not really stuck together very well. And so that sort of affects a lot of their other properties. Usually, the bigger carbon chain you have, the more energy it takes to get it to the next level of the more energy it takes, the more easily it will break its bonds with its neighbors. So, if it's bigger, then that means it's going to have a higher melting point and a higher boiling point. Okay. So think of this as if, bigger things take more energy to get moving faster. Because when things melt, they go from being solid, everybody's packed in one little spot, to moving around more, right? Versus when you're going from a liquid to a gas, that's what your boiling point is. You're kind of moving around and flowing together to completely sort of being disassociated from one another. Packing of molecules will affect this also. So, let me go back to that just a moment. If you have a smaller alkane, its melting point and boiling point will be lower than if you have a big alkane. With boiling point, it really also affects how things sort of pack together, how they sit together, how they flow together in a liquid. These tend to kind of stack together pretty easily. They're going to flow together pretty easily. Remember with this model, here we go. So here's a carbon chain. Ideally it's sort of sitting like this, but in reality he's kind of moving a little bit. Okay, so he's just moving a little bit all over and kind of weaving and wobbling. And so they can kind of weeble wobble together. Okay. Here, if you have the same number of carbons, but one sort of sticking out, you've got a substituent there, these don't pack together very well, do they? So they're going to fall apart more easily. What that means is that there's more energy required to pull these apart than there is to pull these apart. So the boiling point here will be higher than the one over here. Okay, it's also important to think about. So here's our single bond. We're flowing, right? If I show you what a circle looks like, so that's cyclopentane. Guess what? We're not flowing anymore. Things are more rigid, right? So these can pack together more tightly because they're not going to move that much. That actually means that it's going to take even more energy to unpack these because they want to stick together a little bit more. Okay. Next, let's talk about solubility. Solubility, hopefully you've heard the term of like dissolves like. So, makes sense that water and oil don't mix. You all know that, right? So alkanes can be seen sort of as an oil. They're nonpolar. So let's go back to this chart. They're nonpolar. They're not up where water is, right? So they're not going to dissolve each other very much. Their density is actually lower than that of water, so oils will raise to the surface of water. Okay. And alkanes can also combust. So can alkenes and alkynes. We'll talk about that later. But basically, to think about a combustion reaction, what you're doing there is you're burning stuff. You all know that stuff burns that has organic compounds in it. So think of wood. Wood's going to burn, right? Charcoal's going to burn. Oil will burn. If we look at this particular alkane, so we've got 2-methylbutane. That's the way to write it. Another way to write it is like this. Or you can simplify that. And sometimes when balancing equations, it's really nice just to say, yeah, that has 5 carbons and 12 hydrogens. So, I'm going to write out my reaction just like that. That obviously is going to give off some energy because energy is where the fire is that you see. So, here's how I would suggest balancing these. I'm going to start with this guy right here. And I'm going to see how it affects over here. And then I'm going to worry about that. Okay? So I've got 5 carbons over here. Let's worry about carbon only. I'm going to put 5 over here. I've got 12 hydrogen on this side of the equation. Now these come as H2, which means that I need to divide that in half. So that means now I want 6 H2. My carbons are balanced, my hydrogens are balanced. Now let's calculate the number of hydrogen or oxygen we have over here. So here I've got 5 times 2, remember that's 10 oxygen. And over here I've got 6 oxygen. So my total is 16 oxygen. 16 oxygen on this side. This is seen as O2, so divide that in half. And we simply get 8 right there. And that's how you balance a combustion reaction.